Okay, so the title of this talk is Recreational C++. This is basically me having fun, playing around with the language, a few little puzzles and corner cases and things that have amused me over the years. So we'll start with this. What is this? It's a terrible pun. So we got that out of the way. So what is recreational C++? My notion here is I'm playing around with code for fun, because when we play, we're in a great environment to learn. So I'll be solving a lot of well-known problems. I've got nothing inspirational and new as far as I'm aware, but this is kind of what amused and inspired me, and hopefully it will amuse and inspire you to find your own little corner cases and puzzles, and maybe we can share some of those as we go through. I'm describing this as, small. It's lots of more smaller scale problems if you're familiar with the ideas of toys and pets. Toys and pets in development circles are the idea of you've got that little go-to project that every time you have a new environment you need to learn and understand. I'm being exposed to a new operating system for the first time. I'm going to write my familiar little toy, my pet, that I feed and nurture over the years. So that might be something like, a chat application across the network. How does that work in the new environment? Or a classic example, a parser for simple mathematical script. And these are the kinds of things that evolve over years, and they're a much larger scale thing than I'm talking about here. And I'm a careless guardian. I'm afraid all my pets have slowly withered and died. So, because I got too busily hooked up with C++. So what we're going to look at is a bunch of my ideas and things I've just had playing around, essentially implementing little parts of the C++ standard library for the most part. Ideas of coding conventions that come up when you start playing and doing things for yourself. Some C++ trivia corners, because trivia is always fun. How this helps me learn about some of the new language features as they come through. And playing around with the bug reporting systems of various compilers as I push them to breaking point. And some ideas about implementing and testing the standard library. So my own personal bad habit here that I'm confessing up to for those who haven't figured this one out yet is every time I have a new version of the standard, I sit down to re-implement the standard library again. I've never completed it yet, oddly enough, and it gets larger every time. I don't know how I'm going to ever get caught up. The last few times I really didn't get much beyond type traits, tuple, and perhaps I start on the containers and so forth. The thing that kills me these days is I got too good at writing test drivers, and to confidently finish testing something, I can probably finish one type trait before the next standard rolls out. As an example, last time I was writing my test drivers for the type traits, starting with a simple thing like is integral, I had about 10,000 lines of different static assertions for the different types I was trying to test just for that one trait. And I would try that same battery of types on every single trait, so I had a consistent set to test. And that brings up a new problem of how do you audit 10,000 static assertions that they all have the right true or false value? Are you testing what you think you're testing correctly? So I wasn't particularly happy with that iteration, so we go around again, and I start writing metacode to generate my test, and then say, well, is the meta program correct? So I keep chasing my tail on these things. You can see how I never quite get to the end of actually convincing myself I've tested the type traits in order to start on the next component. But it's always fun to start over here, so let's go. Implementing the type traits. Who figured this would be first? We start with type traits because the vast majority of the library, when you're implementing templates, is going to query a trait at some point or somewhere in that implementation. So this is really the ground level of the standard library. It will give us early exposure to testing our traits. Don't worry, I don't have too much on the test drivers here, just insights of what they brought me. So my first design question, thinking about type traits, coming into it new for C++17, is there a minimum overhead kind of implementation I can come up with for the type traits? How can I cut out any of that latent fat that might be there? So this is what I came up with. You can see from the top, we start implementing the, I'm doing the is function trait, and I start with the variable template. Because when I'm doing a lot of my Boolean predicate logic, I want to be querying Boolean values. I don't want to be jumping into types, trying to do funky metaprogramming with types to compute a value and then come back out to the trait. I just want to be in Boolean logic all the way, so I'm going to make the underscore v variable template my primary implementation. And then for the trait at the bottom, you can see I'm now using an alias template for isFunction. It's just the bool constant for isFunction v. So the question is this actually conforming? And what does it buy us? So the rules in the standard say your trait's going to have a base characteristic of integral constant. That was generally assumed to mean will derive publicly and unambiguously from that integral constant type. But my interpretation, as you saw, is I'm going to try and use an alias template. That means I'm actually creating fewer class templates in my code because an alias template doesn't create a new type. Everything is just an alias to just true type or false type. The downside of this, of course, is users are now no longer able to specialize my traits unless they try specializing the underscore v things, which the standard doesn't tell them about because the standard is specified in terms of the regular class type trait. But the standard also tells users they're not allowed to specialize them. So if they try and do that, they'll actually get an error on my system. So I think that's a win. The same computing the underscore v is now my primary system, so I'll have an easier time working in my logic with my traits will be a lot simpler. So this is what you get thinking about these problems. But the only problem is some programs that are actually conforming will fail to compile. If you look at my awkward template here, it derives from isObject_t and isEnumT. So if I have a reference type, both of those are false type, and I've got duplicate base classes, which I'm not allowed. So it's a nice idea that almost but doesn't quite work. But this is recreational C++. How much do I care about that? I'm not shipping a standard library, so I'm going to do things my easy way. Thank you very much. The other thing I did when trying to test to demonstrate the wonderful performance winner me having far fewer actual traits being generated was, I'd write a simple test function with a function template that took in all the traits by const reference and so forth and spewed thousands and thousands of these class templates coming out of my test driver, and I felt very smug because I was trying to emulate the notion of tag dispatch. Because one of the reasons that you have these base characteristics is you want to do tag dispatch by passing a function, your trait name will slice to either true type or false type, and that guides your overload resolution. As soon as I put those actually down to slicing to true type and false type rather than taking the thing in by value and querying the type out, so doing tag dispatch as it would be used, my advantage completely vanished. So it was a nice illusion while it lasted. But I still think it's an easier way to implement these, and it's my library, I can have fun. So this is where we're going to start getting a little bit more participative. We're going to implement the isFunction type trait. So nice thing, we have C++ 11 onwards, we have variadic templates. So the primary trait is an arbitrary type is not a function. And we now have, see if I can make the laser work. First time playing with these things and my aim is terrible. So, okay. We're going to say that, no, my aim really is terrible. Anything that's got a result, the parameter of the form result type, parens, and a list of arguments, and the pack can be empty, that corresponds to everything that can be a function. It's a nice starting point, but how many problems do we see? How many kinds of function is this missing? So I'll start with the first one because I love this piece of syntax. A C-style ellipsis doesn't match a parameter pack, so I need to have this extra signature. And it also means I get 6 dots in a row, which is a wonderful perverse corner. Unfortunately, compilers like to warn you about this. So they're going to make me put an extra comma in there just to silence the stupid compilers. And I think in C++20 we will now be requiring that comma because people had certain problems they wanted to solve with variadic macros, and a certain regularity comes out if this comma ceases to be optional. But that's on the road for C++20, it's not in 17. The requirement's not in 17 yet. What we do get in 17, of course, is exception specifications are part of the type system. So I now need at least 4 of these specializations before my trait is correct. And can we see where this is going? We have these wonderful, what I like to call abominable function types, where the const volatile qualifier is also part of the function type. If you've never met these horrible things, be blissful in your ignorance. But this is what happens when you start playing with your code and people start throwing little test cases at you. This is the type of a member function. It can't be the type of a regular function. You can't make a pointer to these. You can't make a reference to these. You can never actually hold one in your code in a meaningful way, but they're in the type system. Because when you have a pointer to member, the type of the pointer to member points to when you have a CV qualified member function is one of these things. And if you're perverse, you can even declare member functions using this, type defs of these types, but that is really horrible. I don't want to go down that corner. So we've now got these four with the extra ellipses version and the extra no except version. So what is that, 16 now? And then, of course, we've got reference qualifiers were added in C++11 with our value reference qualifiers versions, with the no excepts and the ellipses. And we've now got an awful lot of partial specializations in addition to the primary template, just to try to get our isFunction template correct. This is no longer looking like the neat quick fix that I was hoping that wonderful pack expansion was going to give me. Yeah, recreation can sometimes be frustrating. I've not even spoken about doing the extra specializations for extern C linkage, partly because I've forgotten, I can't remember either way. And we do have problems in certain environments where compilers have their own extensions for function types, like Microsoft's got various declspec calling conventions that also ended up needing specialization here. Perhaps this isn't the right solution after all. Does anyone have an idea how else we might go about this? I'm not going to ask the man there who knows an answer. He's nodding far too happily. Ask the compiler. It'd be great if the compiler gave us an intrinsic for isFunction. That is the best answer. Unfortunately, I'm not a compiler implementer. I'm a library implementer, and I'm working for portable C++. I don't know I'll have that intrinsic on all my compilers. There's a suggestion that we call remove CV. Now, the problem is that CV qualifier on your function type is not actually a CV qualifier. If I call remove CV and pass it one of these strange function types cannot be CV qualified. It's a qualifier on the this pointer when I call the function. So it looks like a CV qualifier. If you play around with macros rather than type defs, you might start getting strange behavior where the compiler tries to treat these things as constant volatile in different places. But no, that's not a CV qualifier. So it's not going to help me, but it is a nice exploration of the type system. Thank you. Okay. This is how Clang solves the problem. Now, I'll be fair, the yellow text is all isObject, and the blue is isReference. So we can collapse this down into just 3 traits. But those traits in turn are composites that are implemented in terms of I've basically inlined the whole operation. So if I'm not a floating point type, an integral type, an enumeration, an array, a pointer, a member pointer, null pet t, a class or a union, void, or any kind of reference, all that's left is I must be a function. And it works. Interesting one is you have to check both isClass and isUnion. The language says unions are class types, but the library says you care about this distinction, so we gave them 2 traits, and isClass will return false for a union. You have to query both. That was another one I learned while going through this wonderful little exercise. But yeah, that works, and it's nice, it fits on the slide, but it's not exactly the simple solution I was looking for, although it's much simpler than 48 different partial specializations. Eric Niebler came up with this really neat solution and posted this online. And I think you can find it on Stack Overflow. Start at the top and the bottom. We're creating this priority tag type, which is a type that recursively inherits, and I say I'm going to have this many different tag types. And so if I've got a tag type, we're going to have 3 or 4 of these overloads. I'll have a tag type 3 derives from tag type 2, derives from tag type 1, derives from tag type 0. So I can plug in the biggest tag type at the top, and it will go down through the overload set and see which thing it matches, which is what we're doing at the bottom. The test is simply saying, is function impl of the size that I get from calling is function impl for my tag type says that's what type of T was going to match. So this is our filtering logic. You can see we're returning arrays of size 1, 2, 3, 4 so we can identify on the size of the return type in the unevaluated decal type context which of these filters got triggered. And then we're using a little trick with SFINI. We're going to have a defaulted template parameter for a bunch of these function templates. And if that function template matches, you're going to get your strongest match, and that is the overload that will be selected. So if we go, see if I can get the laser working. This is going to match, as it says here, all array types. Coming on down, we then say, OK, I've not got an array, because arrays can't be returned from functions. I'll have anything that can be returned from a function, unlike an array. So this will match all other object types, reference types, and so forth in the system. But you might spot there's a problem with abstract types, because you can't return an abstract object type from a function. So we need to filter those before we get down to this set, before we get down to this set. So this is a property-based evaluation to say, we know that function types can't be returned from functions. If I can filter everything else this way, I'm having the compiler do the work for telling me what can come out and is an actual function type. So the match we want to hit is this one at the top. I've got an array of size 1 char, so that's going to match the signature at the end. So that is our is function implementation, which I thought was quite neat. Then we can go back to why was I generating 10,000 different test types to throw at these battery of tests. So we can start with, we're going to have all the fundamental integral built-in types and the CV qualified versions of those, and then pointers to those, and pointers to pointers to those, and CV qualified versions of pointers to those, and then references to those, and to the pointers, and to the pointers to the pointers. Then we can have arrays of all of the above, apart from the references. And we're going to do 2 3-dimensional arrays, because if I've got a recursive implementation of my trait, I want to make sure that that recursion keeps playing through correctly. I've found bugs in implementations of my code in the past by going up to the 3rd, but the 4th and beyond, it was actually catching the recursion issues as long as I went to 3. And in order to support the largest possible type in the type system that Annex B of compiler limitations tells me, I'm allowed a type of up to 2 to the 8, have to support a type of at least 2 to the 18 bytes. So if I make an array of 2, 2, 2, 2, 2, 2, 2, 2, and I have 18 of those, an 18-dimensional array, I can have an 18-dimensional array of chars where each is 2. So I'll test up to 18 dimensions just because, to make sure we're not falling out of any other surprising resource limits. Then we get to function types. So of course, those can go up to 256 arguments with and without ellipses and no except and all those other wonderful things. And we can have pointers and references to those. And we might want those to be taking and returning some interesting arguments. We've also got pointers to members doing this same thing. Then we've got actually getting down to creating the interesting things. We've got enumerations, which can be enum classes or regular enums, or it might just be a forward-declared enum with a fixed base type is a new thing that came in C++11. So these are all different parts of the type system to play with. And then we actually get around to doing the really interesting stuff, which is creating a variety of classes that are perverse in different ways. They've got ambiguous construction if you try and call them with the wrong things. They're move only, they're not movable at all, and so forth. They'll overload the address of operator, but that's much more of a problem deeper down the library. So having a battery of 10,000 test types, what do I learn? Eric's got a bug. In one very odd corner. If he's got an array of an incomplete class type, which is valid in the type system and has to be supported by this meta function, he's going to say that's a function. So yes, I might be utterly insane in the depth of test vocabulary I use, but woo, it does stuff. 13 was just because I thought this was unlucky. But it's a good question. Now I'm getting really obscure and finding something right on the corner. One of the other funny things I found doing this, which has come down to compiler bug reports. I think I was testing his integer at the time, or his enum. Might have been his enum. I had an enum forward declared with a bool as the underlying representation. And it turned out with purely if the enum was forward declared, and only if bool was the underlying type, a debug build of Clang would assert. So they got a nice little bug report and fixed it before the next release went out. Yay me, I fixed a bug nobody else was going to see. Or reported a bug and spent developers' time fixing a bug nobody else was going to see. So this was my approach, which was small enough. Just having got onto Twitter, I actually got to fit it on a single tweet. Yay! So the idea here is function types, as we said earlier, cannot actually have CV qualifiers. So I know that my function type is never const. References have that same property. So I don't want it to be a reference either. And finally, because I know T is not CV qualified, const T, if I have a function type, will still not be CV qualified. So if I check if T and const T are the same, I have a function type. And that passes my battery of tests. And then Johannes Schaub actually got back to me and said, we can actually make this slightly simpler. So this is the final answer, coming down the rabbit hole. I can just check, is const of T const? And that means it solves that whole same thing. So that was really neat. And that really does fit in a single tweet. And then we have the joy of Twitter. Oh, sorry, hang on. Last test. You'll notice everything in that slide was actually simple enough, apart from some of the variable template stuff, to implement in C++98. So this will work for functions of any number of argument types with ellipses and all these things that were really hard to do without just imposing arbitrary limits. So this seemed quite neat. We're actually using this now as our implementation at Bloomberg, having me come down this rabbit hole. I thought that looked really neat. And of course, we're now filing complaints against all our still C++98 and 03 vendors about, gee, you don't handle abominable functions that well, or you're actually allowing CV qualifiers on your references. So it mostly works in 98. It would work if you had a fully conforming 98 compiler, but I'm not sure if any of those ever shipped. I think most conformance came in by the time we had 11. Other than those wonderful folks at EDG, who actually implemented export back in the day. And the other fun thing I had, throwing this against my wonderful battery of tests, of course, is, I don't have. I'm trying to talk to a different slide. I've got another bug report that's coming up. Oh, the other one that's came up with this, unfortunately. Compilers like to warn about ignoring that extra const. So although I've got a nice, neat, short implementation of the trait, it might be very noisy when you compile a large code base against it with lots of useless warnings. Yes, I know it's being ignored. So try benchmarking it. To say, yes, I've got this wonderful, neat, small implementation. It's testing much less than that version out at Clang. It's not doing all the big specializations that the other libraries are doing. And it was very disappointing. Most compilers, even in debug mode, saw through all this and optimized it all away anyway, and I didn't even spot a compile time win, which is what I was hoping for. So while it was a fun exercise, and I'll probably do my implementation this way, I couldn't actually measure a real win from it. But that's okay. that was the goal of Recreational C++. We're having fun and we're learning things, including learning that optimizing the heck out of something, if you've not measured, you're probably not optimizing at all. And this is where I get to find, got an interesting name mangling bug on GCC that was getting collisions on abominable function types, those things with the CV qualifiers, and no except specifications. Because when they put that into the type system, they didn't happen to check whether or not their hashing algorithm for their types, or for the mangling, was going to give a distinct type. But they got it reported in time so that when 7.1 was released, it was already resolved. So hopefully you'll never see that bug. But the joy of playing with crazy things. So this is where Twitter came back to me. As soon as I can fit his function onto a tweet, the next challenge comes back is, can you do his integral? And this one was a lot more fun. And this one I am going to start polling the room a bit more for. So what is an integral type? It's any of that list of 15, specifically that list of 15 types at the top, and any CB qualified variations of those, of course, and any extended integer types that your system supports. It does not include floating point types, enumerations, references to these things, so I've got to make sure I don't accidentally match a reference. It doesn't take pointers to these types, arrays. Types convertible to integer mustn't match either. So how simply can I implement this if I'm going to try a strategy that is not just specialize those 15 types? Try and use it as a non-type template argument. I'm trying to remember where that went. I mean, enums and pointers can be done that way. So it's a start for a filter. It's not the one I chose. Can I try using it as the fixed base of an enum type? Because those, by the language, are required to be integral types. That was exactly where I started. It turns out that's not a spin-I constraint, even with the generalized spin-I rules. So I tried hard on that for days, trying to put that into a spin-I constraint. Doesn't work. Any other ideas? The size of an array. An enum would fit in there, but I could just filter on enum. Did I try that one or not? I have a suspicion I must have tried it, and I'm trying to think what else meant that was unraveling before me. It's not the answer we're going to see, but it's a good try. Because I try to start with the simple things and become more complicated as we go. I have to get back to you on that one. It failed for more than just the enum case. But I can't remember what the other cases were. Yeah. OK. We're going to go with the first step and just try and do is arithmetic. Because if I can do is arithmetic, I can then start filtering down a bit further. So an arithmetic type, those same set of integral types we saw, and the floating point types. It's a subset of the scalar types. So scalar types are those types plus pointer types, enumerations, pointers to members, and null to t. And doesn't include references, classes, and arrays, and so forth. Anyone getting an insight with this yet? Anyone spot anything distinct about the subset of arithmetic types from the other types that make up scalar types? Multiplication. You're jumping about 5 slides ahead. Thank you. Key thing I spotted here is these are all built-in fundamental types, and these are all composite types. Now, one of the properties of a fundamental type is that you cannot overload the operators for it. So let's take a look at unary operator plus. If I write something that will match any type, or provide a unary plus implementation in my namespace for generic type T, that will not be called for any of the fundamental types, but it will match for everything else, or it wasn't a scalar type, and it will not go down the rabbit sense of what we want scalar types to match. So I'm going to have a sniffer function that can detect, did I have a type that allows me to overload unary operator plus? So here we go. I'll have a laser pointer that works, yes. I'll have an operator plus that will match any type. And my primary template, I'm going to have type name void here for a reason we will see shortly, is arithmetic is false. And I'm not going to describe it today, but this is a wonderful addition to C++. Was this 14 or 17? 17? Sorry? 17. Landing in C++ 17 makes creating finite constraints on textual property, semantic properties or syntactical properties of code much, much simpler to create. So if my condition matches, this choice of void is a more specialized template. I lost my mouse pointer. Okay, the lower template is a more specialized template and therefore will match in preference to the primary template. So for anything that has the ability to support, how do we go again? Unary operator plus on a default constructed or value initialized version of that object that doesn't hit this operation because that returns void and I'm not allowed to create. I really wish I could get the hang of pointing this thing. But yeah, I'm making a reference to this, so because my operator returns void, I can't create a reference to void. So this is how I force this finite constraint all the way through. So now I have a syntax that says this will only match for arithmetic types. No, I made a bad assumption. Pointers and arrays also actually, it turns out, to match here. So we're going to have to do a little bit more code to filter those out, and we'll use the multiplication operator, thank you. So with that to filter out the other types, I now make sure that I want to make sure I've not got a user-defined type that implements multiplication, so I've still got to do my test for, was I a fundamental type? But this finally gives me is arithmetic. And it works. So now I want to do is integral. I've already given the slide away, unfortunately. I should have gone one, don't want to jump forward yet. I just need to filter out those float types. And I can do that with the percent operator. Float doesn't support this. Neither do arrays and pointers, so I don't even need this other constraint as well. So now I have is integral implemented as per requested, but in 2 tweets. Sorry. I can only go so far. Though apparently, as of today, I might be able to get it into 1 tweet after all. They're upping the limit. So yep, as I said, this passed all my tests with Clang. It fails for a reason I've not yet figured out on GCC. So I might be ahead of myself in thinking this is a great, perfect solution, or possibly more likely, I prefer to trust the compiler rather than myself, but I might have another bug report I need to file on GCC here. When it starts trying to do this finite constraint on this, calling here, for some reason it's complaining about taking the address of a temporary array. Now, I have no idea why it's trying to take an address of anything. Never mind a temporary array. So I think it's a compiler bug, but I've got no clue where to start reporting other than going, here's some really wacky code. Please find the bug. But that's on my to-do list when I get back to the hotel tonight. I've not tried compiling this with Microsoft Visual C++, unfortunately, because it would all be nice to have a tie break, try another compiler. But the last Visual C++ compiler I had access to before coming out was, I think, VC 2015 and didn't yet have support for variable templates. So I couldn't just quickly plug it in. If somebody else can run that in the meantime, that would be fantastic. Sorry, can you repeat?
Does this not require T to be default?
The question is, does this not require T to be default constructible? And to an extent, the answer is yes. This will only ever match true for a T that is default constructible. And we know that all the types I require it to be supported are default constructible. If T is not default constructible, it's actually going to fail to form these things here in the void T, and that will immediately spin I away. So any type that's not default constructible fails in a spin I-friendly manner and is filtered out. I can't thank Walter enough for this trick, because I thought I'd already solved all the problems in this space. I didn't need this toy, but oh boy, it's so handy once you start using it. It really simplifies things. So, time prompt tells me I might have been, thought I got more content than I did, but we'll keep going and we'll see how quickly we end. Standard pair was my next little point of playing, and we're going to pair through the ages is back into the trivia domain. It turns out every version of the standard we tweak pair in some way, even in C++03. So, in fact, we've changed the signature of make pair, maybe subtly, in every standard until C++17. C++17 did not tweak the signature, but it did clean up the normative wording of what that signature will actually do to fix some holes in the specification that are there. So we didn't get away scot-free, but at least make pair survived ABI intact. So C++98, we take pair with, make pair takes two const references. C++03, we pass by value instead. Can anyone give me a one-line answer for why that might be useful? For 03? If I want to make pair with an auto pointer, I couldn't pass an auto pointer by const reference because I'm going to modify the thing as I move it implicitly. If we pass by value, we support movable types like auto pointer. Of course, for C++11, we're going to go with perfect forwarding because now we actually know how to do real move-only types and get perfect forwarding right. And of course, this broke code, which I think surprised a few people. Anyone know the use cases that this broke? I have silence around the room. Okay, imagine I've got a map, and I'm hearing somebody called it here. Do we want to have take the microphone? Sorry, you're being named and shamed. There. Oh, the answer is it's bound to be a map of some kind. Yes, so I'm trying to insert into a map. I'm going to do make pair. But I could just have created the pair directly, but no, I'm going to do make pair, damn it. And I'm going to make pair because I want to say the first parameter is definitely a string, and I'll deduce a second parameter. So I do make pair string, comma, second as an explicit template parameter to my call. That now means I'm no longer deducing the first argument. It has to be an R value to a string. And if the code I was passing there had an L value, that no longer matches the function call. And there's no easy way to rewrite that function that is saying I really want that to deduce one but not both parameters. So there's a specific idiom there that actually weaseled away in the corner. Although this looks so much better than this, this would have continued working. And are we saving the move? Well, here you have to move in, I guess. So yeah, probably the better answer, but it was an interesting corner that you uncover as you go. For 14, it's simple. We just add const expr. But the puzzle that interests me at the moment is let's implement get, because we've given the tuple API to pair. So the signature is fairly simple. I've got it's const expr function. I'm using the C++17 form of this, which I think looks the same as. No, I think yeah, it looks the same as 14. I think const expr might be new to 17. I can't remember. But we're going to call get on a pair, and we're going to pass an index, and we're going to get either first or second out. And the obvious way you would implement this is using partial specialization on the index, and yes? Sorry? Is integral. We have confirmation works with Visual C++ today. Awesome. So. Test switching back to this. Okay, so the obvious answer here is use partial specialization, with the obvious caveat that you can't specialize function templates. Oops. So we go back to wonderful C++ 98 era technology. We create a class template. In this case, we're calling it pair_util. So I can partially specialize the pair_util function, and therefore within that I can call, I can specialize the whole util for 1 and 0, and just have a function called get within there, and it returns either first or second. And I at least don't need to go through this whole, what's it called, a tuple element syntax, because I know that it's going to be T or U accordingly. So that's a relatively straightforward implementation of get. Any other ideas how I might implement this in C++ 98 era technology, say for standard library TR1? Mentioned it earlier, we can do tag dispatch. So this gets away with a class template and that funky partial specialization. I just have two overloads on 0 and 1, integral constant of 0 and 1. So depending upon your choice of style, this may or may not be simpler. Preferences? My preference is C++ 17. We now have if const expr. So I no longer need to do a dispatch at all. Because although p first and p second are returning different types, so one of those return statements is going to fail to compile, with if const expr, only the desired branch is actually going to be evaluated. So this seems like, a really neat use of the new language, and this is the fun you get when you start implementing pair from first principles every time you get a new standard library. You start finding the new corners where the new language features can go in. But can we get it funkier? There's a strong analogy between pair and tuple. And there's some nice idioms about how we implement tuple that might make this implementation fall out, especially if I can reuse the tuple code so I've got a smaller code base. So the basic notion of a tuple implementation, for those of you who've not implemented tuple before, is I've got a tuple of parameters, and I'm going to want to derive from a wrapper of each element, and that gives me a base, just expand that base class, and I've now got a bunch of, that gives me the data structure for tuple. I've actually got it on the next slide. Basic idea is I'm going to have an implementation class, which I forward declare, and using the C++ 14 type index sequence, which will make me a sequence of 0 to n, or n-1, where n is the number of types in the parameter pack. I will now have two parameter packs here of index and types of exactly the same length. I can just derive from my wrap class, which you'll see on a slide or two, which is indexed by a number and the type. Now, everyone know why I need to wrap with an index number here, rather than just using a base expansion, expand on the types? Perfect answer. If I have a tuple of 2 ints, I can't have repeated base classes. So I need to make sure the types are all distinct, so I just generate an index that lets me count up to them. And then my tuple implementation itself is simply, I derive from that base class using index sequence 4 that will generate this type for me, and inherit my constructors, and it just works. So tuple's actually fairly simple. All the fun is in the constructors and other fun stuff here. That part is not exactly what we're doing for pair, but this is, for example, what our wrap type might look like. I'm going to have a value of type t, whatever I'm wrapping at this index. I'm value initializing it because that's a rule for constructing tuples. We'll talk about the validity of that later. I'm creating a conversion to reference for all the various CB qualifiers I'm going to be interested in. And in order to call get, I really need to get better at my aiming skills. Nope. Way at the bottom there we can see I'm calling my access function with just my tuple. But I'm calling access index n. The access function, haha, I got it almost this time, simply is parameterized on my wrap type with index and whatever type it happens to match. I will deduce the type I match, I give it the index, I slice to that base by reference, and then by returning that value, I call my reference operator overload, and that gives me access to the element. I've got all the different CV or const and reference qualifiers here, or R-value reference qualifiers here, because we overload for those 4 with get calls. We have to ultimately support the whole set. So that's how get works for tuple. It's just this really nice simple slicing function. So can we do something similar for pair? If I implement my pair as 2 wrap base classes, and rather than having value as the data member, I specialize for index 0 and say it's called first, and specialize for the second index and say it's called second, and put the appropriate type defs in there, and appropriately overload the reference function syntaxes, I can now use the exact same implementation that I actually had for tuple. Which seems kind of neat. In fact, I've generalized the whole thing trying to use decal type auto, which I believe is the form to return and preserve the reference on the return type, so I'm not even having to go through the whole tuple element stuff. And you'll notice I'm passing something called tupleish. This will work for tuple, it'll work for pair, it'll work for, it'll not work for array because array doesn't build with this particular scheme. But anything that uses this kind of, I inherit from a bunch of wrappers, I now have one function and it implements all those libraries. So that felt kind of neat. How well does this conform to the standard? I've now got a pair with 2 funky base classes. Does that match and jibe with what the standard says? Was I hearing a no? Why does it not match? The observation is pair is supposed to be standard layout. I do not believe we make that requirement. We indicate that it will look like a struct with 2 members, first and second. But we do not mandate that will be a standard layout struct. We can still have whatever crazy base class implementation details we want to have. I'm not 100% convinced I have the layout guarantees I need that, because it's in a struct with first followed by second, these are 2 public data members of a class, I can do pointer arithmetic between them and so forth. I'm not sure that the standard is required to lay out the class explicitly in the order and with no padding that I would like here. But I think it works. Of course, the next one is, can we go all the way to say, I want to have my pair use the variadic template form? And with C++20, we can. Because now we can say it requires that the size of types is 2. 0 and 1 will not work, 3 or more will not work. This will match only if I have exactly 2 types. And now I've transformed my T and U into a bona fide parameter pack. Why is that a nice idea? It means that I can legitimately exploit my tuple and pair to have the same implementation for all the free functions. So the 6 comparison operators, swap, tuple element and tuple size meta functions, and it turns out that when you get to the get overloads, there's 12 for pair and 8 for tuple, and I just need the 8 overall. So it does give me a smaller, neater solution. Also looks quite bizarre. It's a lot of fun to make. I'm not convinced it's the right answer, but darn, it was fun finding out. Now, don't know whether you picked up whether I have some unusual coding conventions there, or whether some of those are baked into the general notion of how you do modern C++ now. But one of the things I have when I'm playing around with my code is I get to play with coding conventions. And this is one of those things you often take for granted with your code, but if you start thinking about the way you're structuring your code, the choice of layout, of symbols, and how you portray things, it helps you understand what your code is trying to communicate. And to a large extent, software development is about communicating information from the code to the reader coming after you. So I had a little bit of fun. Every time a standard comes out, I try and look for interesting new tweaks and perversions I can do with the syntax. Most of them hopefully are fairly straightforward. Got a choice. I can do if A and B or if A double ampersand B. Who prefers if A and B? I'm looking for a show of hands. I'm seeing a small number of hands. Who prefers if A double ampersand B? I'm seeing substantially more hands. Okay? I'll come to the second one. We've got type def AB or using B is equal to A. These are equivalent syntaxes now since C++11. Who prefers the type def? I'm seeing a small smattering of hands. Who prefers the using? Okay, so C++11 is definitely winning out on the second one. Of course, the first one's both are valid in C++98. I, on the first one, definitely prefer using the AND, because this makes it very clear that I'm reserving double ampersand now to always mean an R-value reference. And I have many more R-value references running around my code than I really would like to be able to grep and see these things quite clearly. Also an old Pascal hand, so AND really didn't surprise me too much. It also means when I see a single ampersand, although that could be confused with a reference, this is much less frequently that you see a bitwise operator. And it means that if I see a single ampersand, I'm not confused whether a double ampersand was meant and accidentally omitted. It's a very deliberate, total change of form of syntax. And I find that actually jumps out and helps me with the clarity of the code. And the question is, wouldn't using bithand also accomplish the same thing? And yes, it would, but yug. And yes, it would mean that ampersand was much more clear to preserve for regular references, but I find the use of bitwise operations in my code base is small enough that the switch of symbology is a much bigger jump to the eye than having bit underscore in front of the AND. Also, you really want your operators to be small between the code that you're joining so I can read the predicates on either side much more clearly. As for the type def I'm using, yeah, when I had type def AB, I always have to stop and pause and go, which way around is this doing the aliasing? And the assignment operator in there, even though it's not an assignment operator, just a symbol, always makes it implicitly clear to me. I liked it so much, I actually went and pushed a change request. The ISO standard is actually available in GitHub if you want to make editorial change requests there. This was a fairly substantial editorial request. You don't want to think about doing anything like this unless you're speaking with the project editors who will be responsible for landing your request. It's not just going to go in for free. But yeah, it was popular enough that actually the C++17 standard is now exclusively using this form in the standard library. So I'm quite pleased about that little thing. And the other problem, of course, being recreational C++, I now get into recreational editing the standard, and I got carried away playing around with the indexes as well. So if you find the indexes of C++17 are a bit better than they used to be, yeah, that's the danger of having this thing available on GitHub now. Other things that come with conventions is our choice of keywords. We're declaring a class template. Do we do template class X or template type name X? Who prefers class? Okay, about half a dozen hands. Who prefers type name? But it's longer. Still seeing a fair number of hands go up. Okay. Next suggestion. Doing a class, a template parameter. Since C++17, we can use type name here as well. So, same question, who prefers class in this context? Few more hands for the familiar syntax. Who wants to move to type name in this syntax, in this convention? Already seeing it's slightly over half the room. So a bit more divide on that one. For any enum class, do I use enum class that we always was proposed in the paper, or the equivalent enum struct just because I can? Who prefers enum class? About 80% of the room. Who would still rather use enum struct because they can? Okay, I see about half a dozen hands there. Last one. Do we prefer, by default, to go with class X or struct X? Who prefers the default to using the class keyword if I'm going to provide member functions and so forth? It's about 70% of the room. Who prefers going with struct anyway? Yeah, about 25–30%. My suggestion is class is always wrong. I would love to deprecate it if I could. This is what I've been doing in my homebrew code now. The reason is, yes, class is shorter. I don't care. Struct, but especially when you come to struct and class, struct has the right defaults because it's going to default to public inheritance, and public inheritance is the right kind of inheritance. I'm inheriting an interface. If I'm using private inheritance, I'm inheriting implementation details, and they're much better encapsulated and hidden using composition. Private inheritance should really be a rarity, and it shouldn't be our default. It also means that when I start listing members of the class, unless I want to go into a private straight away, I'm going to start listing the public interface. And this tells me what I can do with the class. It's information for the user to say, how do I use this thing? So public by default actually tends to be, in my view, when I was coming up with my own coding conventions and thinking and figuring out your value systems, seems to be the right default for me. Now, if you're leading with class and making everything private, you're saying something different. But you are saying something about the values of your code. And you're saying the implementation data structure of how this code composes with other code, and so I can reason about the bits flying around the system and have a much more hands-on implementation level view of the system is what matters to me. And if that is the nature of what matters to you, class probably really is the right thing. And that's the reason we use class at Bloomberg. It's the code I actually work with professionally is going to default to class. And it's actually the right choice for what we do. But by sitting around and playing with this, the idea of recreational C++, you get to better understand what your code's trying to communicate to you. And as I heard from the floor down here, when you come to enum struct, struct is the right answer because it conveys it's all public, which it is. So that's why I go to type name on my templates now. I just want to retire class from my code base entirely. I have no use for it, nor type def. I think the room says it all there. But I did have fun with this, because this is what I found on the internet. I love this. This is fantastic. You'll notice it's C code, not C++, although it is both. It's a funky idea that I can read down to understand I've got the right markers to much more clearly line up which code is where. It's just odd to find that the semicolon terminating this statement is on the next line. But visually, I like my code very two-dimensional. Although this gets a laugh when people see it, I really like it. The problem is I tried writing C++ with it. And we have too many decorators in our type system. So once you go beyond the simple layouts that you're getting with C, I mean, it kind of works, but there's too much noise. I'm not getting the structure out the same as I wanted. It's also a small example, and that doesn't help. But yeah, playing around with syntax is always fun. Another example for playing around with syntax earlier on, Herb was suggesting this back at CppCon, the very first one, I believe. Always auto everywhere, which was a bit more extreme than I was going with my auto usage. So I sat around and I played with it. And I know other people have done this as well. It's a really neat idea. The idea is we've got two ways of declaring my class here. If I use auto, the compiler definitely knows it's going to get the right type. Most of the time I can just deduce and don't have to say anything, but the time that I want to be explicit and say, you really are this type, the notion is that we just construct it on the right-hand side as the right type, and therefore it's going to deduce to be that. So variables are consistently and always introduced by the keyword auto. This basically says variable now. And it gives you a simple, consistent coding style that you can see everywhere. And I believe in C++ 17, someone correct me if I'm wrong, but with the new rules on copylation and so forth being mandatory, I think these two are now genuinely equivalent rather than having an implicit optimization to have to occur there, and the requirement that the type actually be movable. I think this will work even for types that aren't movable now. My experience was that when you're writing function templates, auto is fantastic because deducing the right type that you're getting from your expression, you can't write code to do that at all easily. Loved it. In code that I'm frequently changing, where I don't want to keep jumping in and changing types because it's malleable, I'm evolving, I'm doing, rapid development, iterative, auto is really helpful there. Once I moved to a more stable code base, saying, okay, my library's fairly mature now, I'm testing it, I want this code to be fairly stable, I actually found I liked having explicit types in my type system, and I found this syntax was just a bit too heavyweight for me to get it. But I didn't know until I tried playing with it. And your experience might be different. That's the fun of playing around with your homebrew projects. Play around with coding style. See what comes up. Function declarations, I've got the same overload set 4 different ways here. First one is what you would get from C++ L3. Second one is my first attempt at switching to C++ 11. I just went consistently, let's always use the late specified return type. Third option was, well, a void function doesn't have a return type, so I'll consistently use the late specified return type apart from void, because don't you just know it? It conveniently matches up with auto as having 4 characters. So it preserves the property that all my function names align, which I didn't have in the O3 property. So starting with auto or void gives me a really nice property when I'm trying to read through overload sets. Apparently my session's over, I'll just finish this slide. And the final option, of course, was I could go all the way down and say, well, bool is another 4-character thing, so I don't want to pay the overhead of trying to write this extra thing out the far side. Maybe just 4-character symbols, like char or blessed. And in practice, that's the one I found that worked well for me. Hand at the back. Sorry? Would I do the same thing for long? That would be down in this category. I was playing around with anything that was 4 characters. I would avoid myself doing this, because all I wanted was the everything lining up property. But in practice, I found I preferred the consistency of a result always went on the right-hand side, and void was the exception because there is no result on the right-hand side. And it's a happy chance that it happens to be 4 characters. Would I change this if void becomes regular? No, because void will not become regular, darn it. So I'm done. Last slide for fun, keyword games. I think I wrote it as an April 1st proposal, I can't remember if I submitted it, was the idea that people were looking in around the era of C++, 2008, to have some kind of atomic keyword to introduce atomic variables. And I said, we don't want to introduce a new keyword, we can handle it with existing keywords entirely. Do not break while using this. So then when it came time for acceptance specifications, we have do not throw while using this. So the fun game is, what's the longest sentence you can construct using just keywords? So here I have, a union guy threatening some poor lawyer of, do not try this volatile auto union case or else. And I'm sure you can do better. But notice I'm cheating, I'm using not twice. And with alcohol at the end, thank you. So, we're done.